All right, well, good evening. I hope y'all are going to have a wonderful night tonight. We're going to talk about the OSI network layer, and we're going to get into subnetting tonight, and we'll cover subnetting. Be prepared next Wednesday night. You must be in class, or you will not get your chance for your subnetting test. Um, I'm sorry. Yeah, next Wednesday night. Um, I would highly encourage you to do so and to be here because it will be a pretty interesting test.
You said it's 10% of our grades.
It is 10% of your grade.
It's the difference between a maxing at a B and maxing at an A.
Exactly. So we'll cover network fundamentals, then I will teach you the way I want you to learn to subnet, which is a little different from Cisco. We will go through the Cisco slides, and I'll skip parts of them, and then I'll teach you how you need to subnet. And then as a reminder, after the lecture tonight, it's lab night, so that you can make sure you turned in everything that you need to turn in tonight, since you have 5 and 6 are due, or is it 3, 4, 5, and 6?
3, 4, 5, and 6.
3, 4, 5, and 6 are all due tonight at 11:59. So be sure that you get them in, or else you'll receive a 0. So that's the news for today. Let's talk a little bit about the network layer. Well, what is the network layer? Network layer is responsible for your IP addressing, right? Right? Okay. What it does is it allows to take everything from the layers above it. It encapsulates it with the IP address so we can send it where it needs to go, right? So what you have is what we call packets, right? Protocol data unit for the network layer is called a packet. Now you understand when we say we're going to look at packets through a analyzer, a protocol analyzer, or network analyzer, such as Wireshark, used to be Ethereal, or Ethereal, however you wanted to say it. What is a network layer protocol? It's going to be Internet Protocol. Remember in transport layer we talked about the transmission control protocol, or TCP. IP is what gives you the IP address, and it encapsulates everything into packets. Takes those segments from the transport layer and puts them into packets. Do remember it is connectionless, means there are no connection is established before the sending of the packet. Very similar to UDP in that regard. The best effort is it's unreliable, just like UDP, because there's no connection between the point A and point B, and it's media independent, which means it can transmit over any type of medium. When we're talking about IPs, how do we get from point A to point B? Well, we go through routers, right? And we're going to route our traffic through these routers. And it's going to do what they call the best effort, or the quickest effort to get there. So it could be that you'd lose some packets over the distance. It could run out of time to live. But again, IPs are not connection bound, so therefore if you lose it, you lose it. You don't get a second chance at it, all right? Meaning that it's media independence. It could go over Ethernet, a copper line. It could go over copper serial. It can go over fiber. It can go over copper Ethernet again. It can go over wireless. There's no bounds to what an IP packet can go. There's no specific type of method or medium. So how do we come up with a network layer encapsulation? Well, we have our transport layer where we have our segment header and our data, right? Because we segmented the data from the application layer in the session and presentation layer. We segmented that data, and that's where we come up with the transmission or transport layer. Now, remember, this is what we call a segment, right? Well, now that you add the IP header, which just gives you a source and destination IP address, we're encapsulating it and that's what we call an IP packet. So when you're looking at it through a protocol analyzer, you're actually seeing the IP address it's going to, where it's coming from. Then you can get into the transmission layer and look at the different segments and figure out what segment is how big they're going to be, whether they're 8 bits, 16 bits, they're 1500 bits, how big those segments are broken into. Then you can get down and figure out the data. Does that make sense? So here is an example of an IP header. Now, this 32 bits here that you see actually is what is in front of the segment to form the IP packet. All right. You get the version in the IHL of the IP packet, how long the packet length is going to be, what service type it is. You're going to identify it as gives it service identifiers. Remember, we talked a little bit about those in the last week. Fragmented offset, if we needed to offset it. Time to live, how many hops is it going to be that this packet will before it dies out between point A and point B. What protocol are we using? In this case, it will be IP. If we need a checksum value for verification purposes that the packet didn't have an error, our source address, where are we sending it from, our destination address, where are we sending it to, and any additional options that we wanted to add into this IP packet. And then that extra little byte is for fluff. Okay? But you say, well, it's a 32 bit packet, right? Well, how come I only have 24 bytes? No, if you add them all together. 4 bytes long, 6 bytes dead. What is that?
6 times 4, 24 bytes.
Yeah, why is it only 24, not 32? Because an IP address is 32-bit, not byte. Gotcha. Okay. Now let's talk a little bit about broadcast domains and addressing. What is a broadcast domain? Simply put, it's the area in which, if you were to send out a broadcast packet, all the computers or devices that it would reach. That is a broadcast domain.
Okay. So, for example, the Postal Service has the 56 dot network.
Okay.
So if they had a broadcast domain, everything on the 56 network would get that message. Okay.
If it's all behind that one router. Because for every router, it segments it out.
Okay.
A router is what will stop broadcast domains. Okay? That's why if this floor and this floor are on the same router and this is coming off of a different router, that could be a broadcast domain. That would be a separate broadcast domain from this.
Okay.
All right? List ways in which dividing a large network can increase network performance. For example, if I have let's use Chesapeake as an example. How many computers do you think they have? Tens of thousands. Okay? If I put them all on one network behind one router, could you imagine how overwhelmed that router would be? So, as a network manager, you want to simplify your network and segment them out according to tasks, roles, responsibility, area of responsibilities. You know, put all accounting computers in if they have their own building, have a router there. So everything that's in a broadcast domain inside that building has that one router, and then all those routers interconnect to come out to one main router that leaves. So it simplifies your traffic for your external router. So in this instance, we had a lot of two major LANs. We put a router in between them so that all these don't talk to each other. They have to go through the router, which is outside that broadcast domain, because a switch doesn't separate them. It increases your broadcast domains. because you're adding more and more and more and more to that broadcast domain. Remember, switches just store and forward. How do you increase network security? Well, building A, building B, building C, we could put them out in different segments and they all go out their router, out a firewall to the internet, instead of having to go from here to here and out. The more devices that you put between you and your network, the better off you're going to be. Still in this area, administration and research all have access to the internet. But they're coming out at two separate instances. They don't have that one single point of failure. If you were smart, you would actually put a line in here so that you, between those two routers, so that you'd have redundancy, so anything in students could actually come out researcher if they needed to. You just put them, maybe connect this switch to here and have two VLANs. So you do some load balancing, okay? Now I'll talk a little bit about IP addressing. Remember, IP addressing is just like a post office. It really is. Okay? You have your 4 octets, right? And we're talking about 32-bit IP addressing here. If I wanted to mail a letter from Japan to Jane Doe, 170 West Tasman Drive, San Jose, California, 95134, USA. What is the first thing it's going to look for? USA. Country code, right? Imagine that's octet A. Saying, here's the network in which I'm looking for. San Jose, California would be, or California would give me my B octet. Now I've come down to a region. Okay? San Jose puts me in the 3rd octet. Now I've come down to a city. Correct? And then the D octet gives me the physical address of which I need to get to. So, the letter would come from which country, to which zip code or state, to which address, and to which person. In this case, I'm assuming she's the only one at that address. So in the same regard, we have what we call the network portion and a host portion. All right? Using the 192.168.18.57 network, here, or IP address, I'm sorry. The 192.168.18 represents our network portion. Where am I connected to? That would be your physical address of the 192.168.18 would say, here's the router I need to come into. That's where your physical router address is. And it would probably start with a 0.1. Okay? Your default gateway. If I come up to 192.168.00 or 01, I'm coming into now the region in which this 18th router is at. Does that make sense? Are y'all following me as I backtrack? Lance? Region. It would be like a state. With the 168, I'm in the 168 region. There could be up to 255 routers inside that region to find my local host. Then if I was at the 192.0.0.1, I'm now looking at the 192 domain, right? The entire Class C subnet of the 192 octet. And what that does is it says, okay, I now know that I'm in USA. If USA was 192. Does that make sense? The network host portion, now mind you, this is just a Class C address. Your host portion, .57, is your local person, your local computer, your local device. But how do we get from point A to point B? Well, we go through what we call routing tables. Okay? This is what tells router A out what interface to send this packet to get to that local host. So if I'm on the 10 network, 10.0.0.1 router, and out my serial 00 interface, I have the 172 network. I can see the 172 region or country. On my serial 01, I can see the 192. If we're looking to go back to this 192, 168, 1857 network, right? All I'm doing is saying, I've got to go out with this routing. I don't know where this address is. I don't. So my router has to say, oh, I can see this next router, which would be pointing to that 192 address, out of my interface serial, my serial interface, to get to it. Does that make sense? If I had another router up here, and this one comes into the 172, and this computer, let's just say, is on the 10 network, right? It gets to here, everything behind here on this serial is on the 10 network. It can see everything inside of here because of the switch, because it's on that network. It can't see any host on the 172 or 192 networks. An IP table says, if I have traffic that's trying to go to the 192 network, go out this interface to get to this router. Your next hop will be this router. This router will then take that traffic and say, oh yeah, this is 192, 168. Oh, the .3? Sure, I know where that's at. It's right over here. So it comes down into here, and the switch says, okay, 4 goes out port 21 on my switch. And that's how it gets to you. Does that make sense? Think of a switch as your last mile, okay? It's your postman that's delivering the packet to you. The router is the post office in which that postman works for. Does that make it a little bit better analogy for you? There's a lot of post offices, but if I need to come into this zip code, where does downtown have to route it to? Right? If I'm looking for 130 or 110, it's going to route it to here to the Midwest City Post Office, who sends it out. Oh, it needs to go out to this neighborhood, because that's where this postman's going to go. Goes to this postman, who then says, okay, I'm going to deliver it to this address.
You got this range of addresses, I'm going to drop it off at those addresses.
Exactly. That is all a routing table does. Now, you asked me, what is a default route? A default route, simply put, is 0.0.0.0 going to 0.0.0.0 out whatever interface it's going out of. In other words, all that means is I don't know where the heck to send this, so I'm just going to send it out this port. That's all a default route's for.
Is that the same as default gateway?
No. Default gateway is going to be your connection to this router right here, the router IP address.
Yeah, I remember that.
Okay? When we start programming switches, we will program a default gateway. If you take advanced routing in the fall, we'll be programming those in there, so you'll catch. It changes just a little bit, but you'll get the idea. Okay? So all I did was saying, here's the packet destinated for the 10.111 or 10.110 network coming out or coming from. I'm sorry, it's going to that network, and it's coming out of here, out of the 192.168 network, or we'll just say it's .3 network. And it says, okay, it needs to get out to here. Well, I don't know how to get to the 10 network, but my neighbor over here does. So I'm going to send it over to my neighbor, and he can deliver it. And so when it gets to here, that's one hop. When it gets to here, it's another. And when it gets to that segment, it's a third hop. Does that make sense? So we were talking about the hop count a minute ago. And that's really all it is. It comes out of this local router. That serial interface says, all right, if I need to get to the 110, I'm going to go out, I'm going to find the .1.2. That's all it says. This is what your local router routing table will say. If I'm looking for the 10 network, I don't know how to get there. I just know that 1.2 can handle it. So it's going to go out my 1.1 to get to my 1.2. Confused?
The question that I have
Sure.
is, okay, so .2 has instructions for delivering to the 10,
That is correct.
and it's in my routing table, and so I'm going to set that up to tell the system to say, hey, if you get a 10.10.10.16 number, to look for router .2.
What you'll tell it, and here's all it's going to say is network 10.0.0.0 out this port.
Okay.
That's all you're going to tell it.
Okay.
So it knows, and then when we start getting into dynamic, it'll automatically do this for you, so you don't have to worry about it. I'll teach you static, so you can physically understand how the traffic is routed. First, we talk about the default routes, then we talk about static, then we get into dynamic. Okay? But what you're saying is, if I need to get anywhere in the 10 network, okay, you're not going to have two different line items here. You could, but what it's going to say is, oh, I got .1, got .2. Well, I'm going to knock this to 10.1/16 because it's still going to the same hop. If I had a different router over here that would take it to the 1.2, then I would have two different line items for them. It tries to go up to the highest level to send the traffic.
I have a question. The IP address between these two routers, the computers have to be the same as each other. For example, if there's another computer that is 198.
Okay, no, these are not computers. These are routers.
Oh no, I mean if there's a computer removed thing, and they have to have the same, they cannot be having the same IP address, right?
What, a computer that's over here on this network?
Yeah, and have the same IP address with.
Sure, I can.
You can?
I can add it. Yes. These right here are just private IP addresses. I can have as many millions as I want.
So it doesn't have when they connect together.
Because so long as there's a router in between them, it doesn't matter. It just gets a management nightmare, but you can still do it. Okay? Here's that routing table we're talking about. You see where we got, this is what we call a summarized route, where I have the 10.0.0.0/24, meaning that my 10.1.1 and my 10.1.2 go via the 2.2 network to this hop. They're going out my fast, I'm assuming this is a fast Ethernet because that's what it says. A fast Ethernet line, which you'd never have a fast Ethernet line running from router to router, to get to these networks. So all traffic that's going to either one of these are going to go out my fast Ethernet 00, which connects to the 2.2. That's all it says. I got it? All right, just making sure before I go on. And here's the same thing. What are we talking about when we talk about the purpose and the use of a next hop? The purpose of a next hop is you don't want traffic just sitting there infinitely bouncing around. You want to give it time, and if it expires, then it just dies. Okay? And it's going out this fast Ethernet port. That's really all it amounts to. I'm not going to spend the time to trace it. Dynamic routing, this is what we're talking about. Now, this is just a high level here, so don't get too wrapped up about it. With router A and router B, they have dynamic hops, okay? And router A is configured manually as the next hop for routers or the 2.2 is configured manually. So any traffic coming on the left side of A will go out the 2.1 interface to the 2.2 to get to these over here. It just knows it needs to get over here somewhere. Okay? Router B then takes that comes in from here, says, well, I know where it is. I'm going to configure it to go to here so it can distribute it as it needs to. That's all it does. That's what we call dynamic routing. Now here's the thing about routing. You configure it the way to go, but it does not guarantee the way to come back. All right? Any questions?
What's that? Like 192.168.0.24 means?
That we'll get into that in the subnetting. That's a CIDR number, classless interdomain routing. All right. Alrighty, we're going to continue on talking about network fundamentals and IP addressing, and then I'm going to skip through a couple of these slides that are in here because I don't like the way Cisco teaches it to you. I'm going to teach you my way, and then we'll call it a night. All right. IP addressing, basically, it's just a dotted decimal structure of a binary IP address. It's 4 octets. You type it in numbers you can see in the decimal format, like 192.168.0.1. However, you're not looking at the 11000000 binary, because that would just make everyone's head spin. All right. All an IP address does is it converts it from decimal to binary so that it can do whatever it needs to do for the network and host. Basically, it's going to line up with the position. You start with 2 to the 0, 2 to the 1, up to the 2 to the 7, right? Because you have 8 bits. Each position has a certain value. Starting at 2 to the 7, it's 128. And you work your way down to 1. Okay? And if the bit value is on, then you add the numbers together. If it is a 0, then you don't have a number there. Pretty simple, right? So if I was to add 128, 64, 32, 16, that puts me at 224, or I'm sorry, 240 right there. A 4 and a 1, that gives me 245. Does that make sense? Pretty straightforward right there, isn't it? But you got to do that for 4 octets. All right? And I'm not going to go over that. For 209, what do you think it would be? Simple. What of these numbers together will equal 209? Let's do it together. 128, right? We have to have 128. We have to have 64. That's going to give us 192. So if we're 192,
We need a 16. That'll take us to 208, and then we need the last one. That'll take us to 209.
there you go. Pretty easy, right?
11010001.
Yep. And the difference, while we're talking about a broadcast address, you have your network portion, right? So if we did a 00001010, that gives you 10. And then we did all the zeros here, so we're on the 10.0.0 network. Okay? The network address would be identified as a .0 in the host. .1 would be a host address. .255 in this instance would be the broadcast address, because this network is a full network. So your next network would be 10.0.1.0. Does that make sense? We'll get into it here in just a second. Here is what you can expect for your subnetting test. Where you're going to get me the last octet in binary, the last octet in decimal, and the full address in decimal. Maybe not that, but you'll get, I'll say, give me the last octet of each one of these. And you'll have to tell me what they are. First usable, last usable. The first usable is the network address plus 1. Last usable is the broadcast minus 1. Simple enough. It's not always going to be 254. And I'll explain that when we start getting into more in depth with subnetting. Okay? We have 3 different types of transmissions. You have a limited broadcast, a unicast, and a multicast. Okay? A unicast transmission goes to only one device. Uni. Limited broadcast means I can send it out to a specific destination anywhere on here that I'm looking for. And a multicast means I can send it to multiple people. All right? You don't want to do a limited broadcast. Why? Because it means you're sending it to everybody. It's just a broadcast address. Multicast means you're sending just 2, and uni sends you 1. Multi means not everyone gets it. Several people get it. Uni just means one person will get it. Okay? And what are my private networks? The 10 networks, the 172.16 network, and the 192.168 network. The 10 is the private network for Class A addresses. The 172.16 is the private for Class B addresses. And the 192.168.1 is for C addresses.
That cracks me up.
You never knew that, did you?
No, but it's on a completely separate note. Since I work for the post office, we have a Class A,
Mm-hmm.
we have 56. In all of our processing plants, we have our private networks. It's the 10 network.
Yeah.
I just
Even like my school use 10 network, but most user in the house they use the 192.
Exactly. Remember, Class C address, really, your network goes up to 255 total IP addresses, which means you have 256 addresses. You have 254 usable addresses that you can use. And you have 16 million something in there.
yeah, that just cracks me up.
Okay. Here's what you have. And you will definitely need to know this if I ask this on your subnetting test. Class A, and here's the easy way to remember it. Class A goes from 1 to 127. You have 1 network, 3 host octets. Okay? The default mask, you'll have 255 for whatever your network octets are. Does that make sense? So if you're in B, if you have 2 networks, you have 255, 00. If you are in a Class C, you have 3 networks, so it's 255, 0. These are just default high-level IP addresses. We have 5 classes of addresses. We have A, B, C, D, E. Here's the trick. You start out with 1, right? What does B start with? 128. If I turn on the first bit, 128 and everything else is So if I turn on the next bit, which would be the 64-bit, what do I have? 192. If I turn on the third bit, I have 224. If I turn on the fourth bit, I have 240. Catch it? And that's how they come. That's how they come on. So you have 0, then you have the 1s, then you have the 1-1s, 1-1-1s, and 1-1-1-1s. D is your your multicast. You'll never use it. And then your experimental, which is all your research facilities. They're going to be on the 240 networks. All right. You really want to use a structured process so you can keep a private IP addresses on your internal network versus your public addresses. Why would you want, like you had your 54 network and your 10 network. Your 10s are your private stuff that never gets to see the outside of it. They're always going to be inside. 54s get to see the World Wide Web. So that's your example there of the difference between public and private. They can still go out the same route. They're just going to be blocked by switches, and you're going to have firewalls here. If you don't, I will nail you on a security audit. What is DHCP? Dynamic Host Control Protocol. Means a computer or device will assign you an IP address. They assign you the IP address, the subnet mask, give you the default gateway of how to get out, and whatever your DHCP server is, the device that is assigning you that IP address. Those are the 4 things you're going to get. I'm not going to get into that. If you want an IP address, you are going to go to the IANA, but they're going to refer you to ARIN, which is for the North American area. If you were in any of these other regions, then you would go to these regional internet registries to get your public IP address. All right. You have 3 tiers of ISPs. You have the main internet backbone. You have Sprint, Savvis, all that. Then you get into tier 2, which are going to be your telecom companies, and then you get to tier 3, which is going to be your company. All right. So you're at least 4 steps away from the true internet backbone. I'm not going to go through that. Here's how you subnet. Alrighty. Okay, we have a few simple ways that we can subnet IPv4, and I'm going to go explain these to you. There are many different ways to subnet or to understand the subnetting concept. However, I believe that my cheat sheet is going to be the easiest for you to understand and learn because I took the math out of it. All right? So the first thing that you're going to have to do is draw out these tables. What we have here, the first table, notice I have the 4 octets, A, B, C, and D. Okay? You're going to have a new terminology that you're going to learn. It's called interesting octet, which I will describe in a few minutes. You're going to write out IP address, its subnet mask, the network IP, the first host, the last host, broadcast, and the next network. Okay? If you're borrowing at bit 1, your network increment, so your first network that you would have would be 0, always 0. The next network would be 128 because you're incrementing by 128. Does that make sense for the network increment? So if I'm borrowing 2 bits in on that last octet, which is the second bit, my network is incrementing by 64s. So I have 0, 64, 128, 192 is my 4 networks. You have 0, 64, 128, and 192. Those are my networks. Okay? and so forth and so on. The more bits you borrow, the more networks you can have. Okay? So, example, when you have a live IP address that Cox gives you for the internet, you have 2 live IP addresses that can be assigned to your modem. Okay? Reason being is it can subnet down to right here, the 6th bit. You cannot subnet anything because this would be your network and host, and you can't just have one. And we'll get into that in a little bit. So you'll have 4 addresses. So you have your network address and your broadcast address. That leaves you with 2 live IP addresses. Does that make sense?
Okay.
That's where the 252 is going to come into play when we start between router to router, your point-to-point connections. Your subnet mask will always be 255, 255, 255, 252. I'm getting a little ahead of myself here, but I'm just kind of pointing this out so you can start to see how the picture is going to come. When I talked about the interesting octet, all right, on the subnet mask line, right here, if our interesting octet is D, everything in the subnet mask line will be 255s straight across. So 255, 255, 255, and then whatever we have in our interesting octet, which would be our subnet interesting octet mask, the mask value. All right? I'm just trying to give you so you can kind of see where I'm coming up with the flow. So first things first, we have, usually you get an IP address in a block, okay? For example, 172.0.0.0.0 network/20, which means your subnet mask would be a 255, 255, 240.0. Why? Because /20, your CIDR number, means that you're borrowing. Remember, we have a 32-bit address, right? Each of them have octet 8 bits. So if I take my CIDR number /20, take 20 minus 8, what do I have? So I got 12 minus 8, I got what? So 4 bits in this octet. Anything to the left of that interesting octet is what? It would be a 255 in the subnet mask, right? I have my interesting octet, and then the thing says to the right, any octet to the right of it would be a 0. So if I'm borrowing my 4th bit, I have 128.64, right? Which is what?
192.
Then I add 32 to that.
No, so it's
224.
Yeah,
Add 16 because I borrowed right there, right? And then I have 8, 4, 2, 1. So what would that give me? Now you see where it's coming from, right? It's just an example. So what we're going to do is we're going to take the IP address of a 192.168.10.0, and we're going to look at the CIDR of /29. So first things first, we're going to put in our IP address, right, on the IP address line, the IP that we have, which is 192.168.10.0, right? Now, I need to say, if I'm looking at 29, okay, we got 29, right? If I have my 8s, what do I have? 29 minus 8 leaves me what? What does that leave me?
13.
That leaves me
5.
5. So my subnet mask then for that line is going to be a 255, 255, 255. Remember, like I said, this is our interesting octet, right?
Yeah.
Anything to the left of it is 255. So now if I'm borrowing to the 5th bit, we already know that what was our 4th bit?
240.
So if I've got 240 and then I'm looking at the last 4, and I've already here, what do I have now? A 248, right? Right? So, all I did was take the 29 minus 8, which gave me 21, took out another 8, gave me 13, took out another 8, gave me 5. So I'm looking at 5. The 5th octet means my networks are going to increment by a value of 8. So my first... So what I have now, just to make it a little easier for you so you can kind of see where I'm going with this, I put some spaces out here. My first number is going to always be 0. Always. Okay? Because I start out with a 0 for my network, no matter where I'm at. What is my network value, or my network increment? 8. Correct? What's after 8?
16, 32,
Eh?
24.
Right? So, what we're looking for, now that we have identified our network increment of 8 and our subnet mask value for the interesting octet is 248, we're looking for what are we doing? What is our network incrementing by? So we had 0, then we had 8, then we had 16, 24, 32, 40, 48, so forth, so on, right? Meaning that you would have a 192.168.10, 0, 192.168.10, 8, 192.168.10, 16, so forth and so on. Because those are my networks.
Okay.
Makes it a network address. So we can fill it in. We filled in our subnet mask right here on the board, right? Our 248, remember our little asterisks here, we got that from that subnet table that we just did in step 4. Now, or step 3, that gave us our subnet. Now we take out and put in our IP address. If you have a 255, this number is going to come all the way down. This number would come all the way down, and this number would come all the way down. Okay? So 248, my host is a 0 in this instance, right? So this is my network address, correct?
Yeah.
So what do you think would be my first host? Armand, what do you think?
92.168.10.1.
Very good. That is my first host. Because your first host adds 1 IP to your network address.
So it's 192.168.10.8?
No, 10.1.
10.1, okay.
Okay? Now my last host is going to be 1 less than my broadcast address. My broadcast address is going to be 1 less than my next network. So what is my next network address? Remember, what are we incrementing by for our networks? 8. So what would this next network address be? What do you think?
Is it going to be 192.168.10.9?
No, it'd be 10.8. That's a network address.
Okay.
The first host on that one would be .9,
Okay.
which we'll get to here in just a second. The broadcast address then is 1 less than the .8, which would make it what?
.7.
Exactly. So then the last available host, which would be
6.
.6. So here's just a little way of doing this. Let me get down here so you can see. Remember, we were in our D-octet, right? And I'm going to change some of this information right here. Our next network address is going to be our A value, which is right here. This should be A plus 1, by the way. our A value plus our increment. So if we had 0 here and our increment's 8, that would be 8. My next network address minus 1 would be .7. My next network address minus 2 would be .6. So here's how you filled in the table. How easy is that? Come on, David, tell me.
It's going to take some practice.
Okay, with everything.
It's math. I mean, so it's not end of the world, but it's math. So it'll take some work.
Okay.
But all good things come from work.
Now I'm going to show you a little bit something different. Let's go back up here. What happens if it's in the C octet? If this is my interesting octet. Again, that needs to be A plus 1. If, like I said, if our interesting octet is C, everything to the left of the C octet, which means octet A and B, in the subnet mask would be what? 255s. Anything to the right is going to be a 0. Now here's the cool thing. No matter what you do, if you're in the B, if your interesting octet is a B or a C, these numbers will always be the same. If your CIDR number is less than 24, those will always be your ending IP addresses. Always. Okay? You with me? No?
Yeah.
Okay. Now, here's what happens if you're in the B octet. You just add this is 255s right there, put zeros up top, and that will always be the same in C and D.
Behind all of
If you're an interesting octet as B, these will always be your answers in C and D.
Now, the question I have is what defines the interesting octet?
Your CIDR number,
Okay.
your bit value where you're breaking it out.
Okay.
Like we had 29, we we took out 8.
Yeah.
Here's our interesting octet. This is where all our math is going to be concentrated in this octet.
Okay.
You can't subnet the class A. Or A octet, I should say.
Yeah.
You can't subnet in there. It's impossible.
No, it tells you what country to go to.
Exactly. So that gives you that. Now, with every rule, there's always what?
There's always an exception.
There's always an exception. And the exception for this one is that when you're in class D, or octet D, if you're at the end or your last true network segment, your next network will increase by 1. So notice that's an 11, not a 10. That's the only exception. So if you fill this all the way up, so I had 285, 285, that would be 0, that would be 0, that would be a 1. You add 1 to this number. Does that make sense?
Yeah.
That's the only exception, is that when you're end up being in that last octet, your next network will be 1 network higher in the octet to the left. And that is subnetting in a nutshell. I told you I simplified it. Beats counting bits, doesn't it?
Yeah, it does.
But so long as you fill out this table, you're good. Now comes the fun part. Is there any questions? And I'll look at you, David, because
No,
you seem to.
Because I get this quiz on my face.
Armand, you get it? If you followed step by step through the subnetting, Just come up with your own numbers and play with it. That's the only way you're going to learn it.
So, okay. So, for example, in our homework assignment number 6,
Okay.
it says, you've been given an IP address block, and it tells me the IP address block.
Uh-huh.
And it says, you must provide for existing networks as well as future growth.
Mm-hmm.
So, the first subnet, existing student LAN off of router R2, which is in our
Uh-huh.
table, up to 60 hosts.
Right.
So am I going to come up with 60 IP addresses?
Now, what is your, you have eight digits, right? 8 bits?
Yeah.
Okay, we have 1, 2, 4, 8, 16, 32, 64, 128, right?
That's correct.
What number is higher?
128 is the highest.
No, you needed 60.
Okay. Yeah, 60 up to 60 hosts.
So where am I gonna cut it off?
64.
Okay.
So that tells me that's gonna be, I'm gonna have x.x.x.192 is my subnet. X meaning 255. It's just my shorthand.
Okay.
Because these two will be a network portion. All these will be my host. So that after all these are turned on to 1, my next one that I need to flip up would turn this one on, and all those go back to 0.
Okay.
Okay, but that gives me 60 hosts that you can actually deal with.
Yeah, I can hook up.
Or 62 hosts that you can actually deal with, because one will be broadcast, one will be network. And so that gives you 2 more for growth, but you still have
The 60 that's
exactly.
okay.
And so if you needed, what's the next number?
28.
28. Where would you be?
That's 32.
So then what do I have?
224. Okay.
Does that make sense now?
Yeah. Yeah. Oh, that's
And that's all it means.
and so for each, so I can so what you're saying is that with that formula, I can define each subnet
Exactly.
as being the subnet is going to be whatever, you know.
Uh-huh.
Okay. Okay.
And we can find the IP address.
And then when we start getting into VLSM here in a little bit, you're going to start with a range. It'll just say 192.168.0.0/24.
Yeah.
So then it says subnet this out. You have 5,000 hosts on this one, 4,000 hosts on this host or router, 3,000 hosts on this router, and 2,000 hosts on this router. Now subnet it out. So what you do is you go up to the 192.168, and you'd have 16 digits out.
Okay.
You keep, remember, every number going up keeps doubling.
Yeah.
So you'd find the number the next number to the left of it that would be higher than what you're looking for.
Okay.
That's your break point, and that becomes your interesting octet, wherever you break it in.
Okay.
And then you start, and then whenever you end that one, that's going to be your start network address for your next smallest network. You start with the biggest network and you work your way down. Does that make sense?
Yeah.
Is everyone with me?
Yeah. I just want to work through some of these. I want to get good at